Alright class, let's look at learning objective 2-5. Relate graphs of position, velocity, and acceleration versus time to free body diagrams. Let's think about that for an example. A graph of like maybe a velocity versus time graph, you're going to relate that to a free body diagram. Remember, these guys show us all the forces, I'll make a little dot, acting on an object. Maybe this object experiences a force to the right of 2 newtons, and you're going to think about what that object's velocity versus time graph would look like. So you're going to be relating those two things. Now, Newton's first law, you probably remember this at the top of your head. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest unless acted upon by an outside force. That's Newton's first law. Let's fill that in. Objects in motion. So if it's moving, it's going to stay in motion. And objects at rest tend to stay at rest unless acted upon by an outside force. Before we move on, let's just jump really quickly where it says or. Or objects move at a constant velocity unless they experience a net force. That's the high school version of Newton's first law. I think that's a better way to say it. Objects move at a constant velocity. A constant velocity. Their velocity will not increase, decrease. It will stay the same unless they experience a net force. And a net force is any unbalanced force pushing on that object. So let's look at this example. The hockey puck experiences no friction, so it keeps going. So after this hockey puck gets hit and it has a velocity moving to the right, after it gets bumped, it is now just going to be at a constant velocity. It'll feel a normal force in the upward direction. It'll feel a force due to gravity in the downward direction. But the magnitude of these forces, those arrows are the same length, so those forces are balanced. And it will just experience this constant velocity here. It's not going to speed up or slow down because we're assuming that on this hockey table that there's no force of friction slowing this thing down. If we look at our car here, it seems Mr. LaForge has left his cup of coffee on the top of his car, and his coffee on his car will stay at rest. Obviously, as soon as he drives away, this coffee, let me draw that a different way. As soon as Mr. LaForge drives away, this coffee, it's going to stay put, which is bad news because if there's no car underneath, this coffee is going to fall straight to the ground at a rate of 9.81 meters per second squared. So remember, objects move at a constant velocity unless they experience a net force. And we have a little comic here. Wait a second, but there's no net force on me and I'm not at a constant velocity. This guy thinks that he's not at a constant velocity, but if you think about a student on Earth, he really is. He's got a constant speed of moving around planet Earth. So he actually might be moving, or Earth is moving, rather, and he's on there. Net force. When the forces in one direction are greater than the forces in the opposite direction, the difference between them is called a net force. When the forces in one direction are greater than the forces in another direction, that was a weird thing that happened, are greater than the forces in the opposite direction, there's the bell, the difference between them is called a net force. So let's look at these examples. there is a force in the upward direction of 2 newtons and a force in the downward direction of 2 newtons. These forces are balanced. These are balanced, which means there is no net force. These forces are balanced. There is no net force. But we look at this example. Here's our object, and it experiences a force in the upward direction of 3 newtons and a force in the downward direction of 2 newtons. It appears that there is a difference, so it experiences a net force of 1 newton. 1 newton in the upward direction, which is probably going to be the positive direction. So you could say something like, let me see if this will work. Oh. The object experiences a net force in the of 1 newton in the positive upward direction. Super specific. Oh my gosh. I love being specific in physics. It makes things super clear. Okay, let's look at this example right here. So yeah, the object experiences a net force of, maybe I'm not so clear. Let me get there. Of 1 newton in the upward direction, in the positive upward direction. That's perfect. Now we have this little free body diagram here. We got 2 newtons up, 2 newtons down, and 2 newtons to the left. You're like, oh my gosh, 2 newtons, 2 newtons, 2 newtons, totally balanced. Not quite. We're balanced in this axis, the up and down, but we're unbalanced to the left. So this guy has a net force of 2 newtons to the left. So this object experiences a net force of 2 newtons to the left, which is probably the negative direction. So 2 newtons in the negative direction experiences a net force. Now, and that tells you how it's going to accelerate. Now here's another one. So we have 3 newtons up, 3 newtons down, 2 newtons right, 2 newtons left. These forces are balanced. There is, wow, that was bad handwriting. Sorry, team. These forces are balanced. There is balance in the force.